Okay, so we're just going to look at the two questions you struggle with, especially 13B, I, and 13C, I, and I, and also question 14. So looking at question number 13, this first graph is an example of a displacement graph displayed in the X and the Y direction, okay, D and X, whereas this here is a reflection of the compressions and rarefactions of particles along a line. Okay, so this is when t equals 0, there is no wave passing by. Okay, so BI says copy the diagram, immediately below the copied line draw another line. So what we do is we draw that other line, okay, we label it 0 to 8 with 4 in the middle and 2 there and 6 roughly, okay. And we'll just change the color slightly so you can see the dots. So what we've got here is essentially when the pressure is starts to become maximum and the pressure starts to become a minimum. So it's basically the start. Here is a start of a compression, and here is the beginning of a rarefaction. Okay, so how do we show that in this number line? Well, you'll notice at point number 0, we're at equilibrium, so that's fine. And also at point 8, we are at equilibrium. Okay, 8 minutes into the length of the longitudinal wave. However, at point 2, okay, you'll notice that the particles are going to start to bunch together a lot more, because that's going to be the start of our compression. Okay, and that's going to continue on. Okay. There we go. Continue on from 1.5 to about 5.5. Okay, so that's the start. That's the peak. So that's going to be an example of, say, this part here. Okay. That's going to be the compression. Okay, compression of the wave when it's all bunched together. Okay, that all the particles are bunched together, and the epicenter of that particular bunching up is going to be at 4 centimeters. Okay, that's the answer for the second part, 4. Right, so that's part B, I and I. Okay, so it's going to be indicating the diagram position of the compression. It's going to be between 1.5 and 5.5. Okay, that's the compression. So indicate. So now what we're going to do is going to repeat this number line, BI, to show the positions of these molecules at T equals. You go 2, 4, 6. At T equals 1. Okay, so all that's going to happen is that you're going to be moving things along by 1 second. Okay, so it means that now the equilibrium position in what was 0 is now at 1, and now we've got bunched up, bunched up, bunched up, bunched up, bunched up, bunched up. Okay, and bunched up, bunched up, and now a little bit on there. So now that's at 9 seconds, and we have that final one here. It's not quite there. Probably it's going to be about here. Okay, so the compression has moved along, and you can just see basically the timeline has, or the line has moved on by 1 second. So the points that were at 0 are now at 1. Okay, And now the compression, instead of being at 4, has moved along to being at 5 centimeters. Because the whole compression has moved on by 1 particular centimeter every second. So that's the answer for 13 CI and II. Now the graph also shows the variation of distance with displacement of air molecules. The sound waves travel through the air. Positive displacement means the motion is to the right, and the speed of sound in air is 340 meters per second. So determining the frequency of the sound wave, well, frequency will equal velocity over wavelength. So in our question, it's been given the velocity of sound in air is 340. The wavelength is going to be determined now by working out the wavelength. Okay, so the wavelength is the thing that has to be determined, and the wavelength from our graph is going to be 0.4 meters. Okay, because that's the time between compressions. Okay, so if we put that in, 0.4 equals 850. Ooh, not very neat. 850 hertz. How did we get 0.4 meters? Well, it's essentially the distance between the wave formations. Right, so B, a compression occurs every, state the distance x when, which is a compression, and when a rarefaction occurs. Okay, so again, looking at our two diagrams here, actually not looking at two diagrams, we're looking now on question 14. So how do we get, so how do we get a wavelength of 0.4? Okay, that's how we got it there. So it's going to be 0. That's the wavelength there. Okay. And how did we come to the conclusion around when the compression occurs? Okay, it's around about 0.3. Okay, this distance here. Okay, 0.3. Because molecules just to the left of this point have a positive displacement, and so move to the right. Molecules just to the right move to the left, causing a compression of 0.3 meters. Okay, and by similar reasoning, the distance x in which compression occurs is a point. 0.1 meters is a point where rarefaction will occur. So that's point BI22. So compression occurs every 0.3 meters. Okay. And a rarefaction occurs every 0.1 meter, as you can again see from this developing graph here. So hopefully that's helped you answer those particular questions.